let's put everything we have figured out about convolution and Dirac deltas and everything else, let's put it all together in an application. And this is actually a pretty sophisticated application. What we're going to do is try to prevent echo in a video conferencing application. So in a video conferencing application, there's a connection to the outside world. Maybe it's a telephone wire or an internet connection. And it comes to our side of the connection and makes some sound, right? This is hooked up to a speaker. And this is all happening in some big room, right? And there's a person in the room. And there's also a microphone. This is how I'm going to draw a microphone, I guess. And the microphone records an audio connection. And what we want to do is the sound coming from the other end of the connection, we want to put it out in the speaker. The microphone should hear the sounds that this person is making and then send that sound back across the wire. But there's actually a problem with just taking whatever this microphone picks up and sending it back across the wire. The problem is this microphone is going to hear not only this person, but also this microphone is going to hear the echo of the sound coming out of the speaker. And we don't want to send that echo back across this connection, because if we send this echo back across this connection, on the other side of this connection, it'll come out the speaker and then come in the microphone on that side of the connection and then come back to this side of the connection. And we'll get this sort of infinite loop of echoing. And that sounds like it would make for a pretty bad video conference. So, so what we need to do is somehow, whatever this microphone picks up, this microphone will hear the echo. There's nothing we can stop about that. But before we send that across the wire, we have to somehow remove that echo so that what we're sending back across the wire is only what this person is saying. So let's name all of the sound signals involved. Maybe whatever's coming out of the speaker, let's call that S of t for speaker. And what this person is saying, let's call that P of t. And what the microphone picks up, let's call that M of t. Okay. And so inside the, say there's some computer here or some system. The system knows S of t, and it knows M of t because it knows S of t because that's coming across the wire. This system knows M of t because that's coming in from the microphone. But the system here does not know P of t. P of t is what we want to send across the wire. So what we have to do is, knowing M of t and S of t, we have to figure out P of t, or at least some reasonable approximation of P of t. Well, there's a function I haven't named here, which is the echo, right? After this sound bounces, the sound coming out of the speaker bounces around the room, then the microphone picks it up, and that part of the sound, maybe we could call E of t. E is maybe a dangerous letter to use, but we aren't going to need exponentials in this, so I'll just use E of t. And E is the echo, right? So the sound that the microphone picks up is E of t plus P of t, right? So what we would like to do is send across the wire M of t minus E of t, because this difference is, according to the equation above here, this difference is P of t, what the person is saying, and that's what we would like to send. But the problem here is, remember, our system knows what the microphone is picking up, and it knows S. The system doesn't know what this echo is, unless we do some sort of fancy math to figure that out. So the problem here, the problem that we have set for ourselves is we know S. We want to find, or predict, maybe would be a better word. We want to predict what the echo will be. Because if we know the echo, then we can subtract it from what the mic picks up, and we'll know what the person is saying, and we can send that across the wire. All right. So this is the problem we have before us. Knowing what the speaker is putting out, predict what the echo should sound like. Well, this room acts like a linear system. The way you can tell it acts like a linear system is if you imagine not playing anything in the speaker, so not driving the system at all. So if you have a freely oscillating room, uh, the sorts of sound waves that can exist, if you have two sound waves that can exist in this room, if you add those two sound waves together, you get another sound wave that could exist in this room. That means that whatever solutions there are to sound in this room, it's linear. And that means this room acts like a linear differential operator. So uh, S and E aren't completely unrelated. They're joined by a linear differential operator. So S is really a driving function for a linear differential system. So um, since we don't know the order of the linear differential system or what any of the coefficients are, I'll just use L for the linear differential operator that is the room. Okay, so how is it that E and S are linked? Well, S is acting like a forcing function because it's an input to this system, and E is the result of the system. It's the behavior of the system or the resulting sound wave if you drive this acoustic system using S as a forcing function. So the relationship between S and E is that the linear differential operator applied to E has to be S, right? This looks just like say y double prime plus y equals f of t, right? In your mass spring kind of situation, y would be the resulting behavior of the mass, f is your input signal, and so the link between these is that f is your input and y is your output. Well, this is the same kind of situation. It's just that we don't know what this linear differential operator is. But we do know the fact that it's linear, though, and that's the important thing. So for linear differential systems like this, we actually know what sort of solutions can happen. So solutions to a linear differential equation like this always look like, so the solution, the echo, is always your driving or your forcing function convolved with the impulse response. I'm not sure what to call the impulse response. Let me call it maybe E sub IR for the impulse response, and it's an echo. So, this convolution, there are nice algorithms for computing convolutions of sound signals, especially if you're talking about uh, uh, discrete sound signals like a computer would deal with, as opposed to continuous. So there are good algorithms for computing convolutions if you know these two things. Well, remember, our system, our box up here, does know S because S is what's coming out of the speaker, and so the system knows S because it has to play the sound, so it knows S. But we don't know the impulse response. If we did, we could just compute this convolution and we'd know what the echo sounded like. So now we've reduced the problem further, right? First, we were trying to figure out what the echo sounds like, but now we're just trying to figure out what this impulse response sounds like. Well, what is the impulse response? Remember, the impulse response is the solution to this equation. Your linear differential operator applied to the impulse response is supposed to be equal to delta of t. This is the definition of the impulse response. It is the resulting behavior of the system when the input to the system is an impulse, a Dirac delta. So how can we find this? Well, we don't know what the linear differential operator is. So there's no hope of solving this using this equation. But we can measure this because we don't know sort of what this linear differential operator is. But remember, this linear differential operator comes from the room, and we have access to the room because we can play sounds into the room. So what we can do is, in our speaker system, right? Remember, we have a speaker and a microphone. What we can do is play over the speaker, we can play an impulse. play a Dirac delta and then listen to the response. But we said earlier that what comes out of this speaker and the echo that comes into the microphone are related by this equation. So if we play a Dirac delta, what the microphone will hear, assuming there's no one else making noise in the room, if we play a Dirac delta, what this microphone will hear is the impulse response. So all we need to do is find a split second, maybe a second or two of silence, play a Dirac delta sound, and we can record the impulse response. Well, how do you play a Dirac delta? I mean, remember, the graph of a Dirac delta is it's zero everywhere except at the origin, where it's infinitely tall. Well, we can't actually play that with a speaker. Our speaker would break if we tried to stuff this signal into it. But what we can do is approximate the Dirac delta. So we can play an ultrasonic chirp, essentially, a very quick chirp of sound that takes the smallest bit of sound that we can put out with this speaker, the smallest time slice. So that is an approximation for delta. So the echo that we get back won't exactly be the impulse response, but it will be a reasonable approximation. So using this trick, we can measure the impulse response. Essentially, we can record it. And now that we know the impulse response, because we measured it, we recorded it, then we can take the sound that we're going to put into the speaker. This is the sound coming over the wire. Convolve that with the impulse response, and that tells us the echo. And now that we know the echo, we can take the total sound that the microphone records. We can subtract the echo, and that will tell us the sound that the person is making. And remember, this is what we will send out over the wire to the other end of the connection. And so we've successfully, just by measuring the impulse response, convolving with the sound that we're going to play with the speaker, we can use that to subtract the echo, extract the sound from the person, and communicate that to the other side of this connection. So just a little bit of knowledge about convolution and linear differential systems lets us solve this echo problem in a really elegant way.